Hi, and welcome to the Onset introduction of the RE4AFAGRi project. Onset is the open source spatial electrification toolkit, which forms a key part of the RE4AFAGRi integrated modeling framework, and here we will take you through the purpose and basic functioning of Onset. The challenge we're facing in sub-Saharan African agriculture is significant. More than 80% of the agricultural production in sub-Saharan Africa comes from smallholder farmers specifically. And more than half of the total population depends directly on agriculture as their main income source. Furthermore, almost 90% of this cropland is rain-fed, waiting for the rain, instead of using modern forms of irrigation. Additionally, most communities do not have electricity, they have low productivity, and crops are often sold raw or wholesale with no cold storage or crop processing capabilities. And unfortunately, many of these Africans get stuck in poverty and inequality traps with additional pressure on their food security. Luckily, solutions do exist with many opportunities for development, and the RE4AFAGRi project aims to explore these, such as sustainable irrigation and community-wide renewable electricity access, increased productivity and local crop processing for value add, and agriculture to leverage reduction of poverty and inequality. All surrounding this is the essential need for affordable and clean electricity, however. Then the question becomes, which solutions are the best, or where are they the best, and what will all of this cost? To answer this question more fully and accurately, we together have developed the multi-model integrated RE4AFAGRi modeling platform. Here we integrate 4 different models, including water crop, looking at water needs and constraints across the continent, MLED, which looks at electricity demand for all different sectors, the NEST model, which looks at long-term scenarios and investment requirements, and Onset, which is the focus of this talk today, which looks at the specific supply option optimization of individual communities across a country or continent. The geospatial energy access planning problem has many different challenges, however, with also many different opportunities. There are several supply technology options available, including centralized grid extension, mini-grids, and standalone systems. This also needs many different data sources and scenarios such as population, energy resources, infrastructure, demand, and costs. Doing this in a very often data-scarce environment and planning for scenarios of a very uncertain future. Gladly, many new modeling techniques and data have become available, including satellite image processing, machine learning, which have revolutionized possibilities and widespread data availability, and multi-scale modern integrated platforms such as the RE4AFAGRi system presented today using Onset and other soft link models. Many options exist for providing electricity access to communities across the world, but they can generally be categorized into 3 different sections, including centralized grid extension, which also requires the supporting generation capacity and grid extension, standalone systems such as solar home systems, solar lanterns, or diesel generators, and also mini-grids, which include local generation and distribution systems, typically solar, but also hydro, diesel, wind, and hybrid combinations of all 3 of these. These can provide many different energy services across the chain, including sometimes more services where energy efficient devices are used. So many solutions exist, but which ones are the best? Where should we deploy them? How much will they cost? And when should we do these? For every single community across the world, they have different local contextual situations, including how far away are they from the existing grid network, What resources do they have nearby, including hydro, wind, and solar? How many people live there? What is electricity demand? What kind of activities exist, etc. And the list goes on. This question then also needs to be asked for every single community that does not yet have electricity. How do we do this? OnSSET system is one of the main ways that we answer this question. Onset stands for the Open Source Spatial Electrification Toolkit. It's been developed by many different institutions across the world, including reputable organizations such as the World Bank, KTH, United Nations, International Energy Agency, NASA, and many, many others. Onset is a GIS-based optimization tool that supports electrification planning across countries and regions to determine and reach energy access goals. It combines and uses many different geospatial data sets, and at the settlement level can help to determine energy access solutions. It combines energy demand, population distribution, energy resources, proximity to energy and transport infrastructure, and all of the different cost and performance parameters of different energy technologies included, such as those of individual systems, mini-grids, grids, etc. Onset has already also proven its value in its use by many reputable organizations around the world, such as the International Energy Agency, looking at continent-wide electrification options, the World Bank ESMAP Group in their mini-grids for 500 million people, and the Africa Energy Outlook. Onset is therefore the perfect tool to answer our question posed earlier for which settlements should get which options. Using the geospatial processing and least cost supply modeling, the capabilities of Onset, we can answer this question for every settlement in a region or country. So what does this actually look like? Here we can see an example for Zambia, including in the SDG 7 Universal Access by 2030 scenario. Which solutions would be the best for over hundreds of thousands of individual population clusters across Zambia in the year 2030? In the map shown below, we can see this scenario plotted out. In the blue, we have where grid extension is expected to be the least cost option. In yellow, where standalone solar home systems are expected to be the least cost option. And in green, where solar hybrid mini-grids are expected to be the most cost-effective option. Onset also provides us much more information than just which options are expected to be the least cost. It explains for each and every population cluster model how much population is expected to be there in each year, the electricity demand from the different sectors, the electrification status, how many new connections might be required, the installed capacity of those connections, investment requirements, as well as the levelized cost of energy expected in each of these locations for each and every option investigated. To get Onset running on your computer, you will first need to make sure that you can meet the software and data requirements. The RE4AFAGRi implementation of Onset was developed and tested on a 64-bit Windows 11 environment connected to the internet. It's written in Python programming language. Detailed installation instructions are included in the next videos. The minimum requirements can be generally described as requiring Anaconda for the Python package environment management, to get and install the RE4AFAGRi implementation of Onset from the GitHub repository, to download the required model input data from Zenodo, and more info and help can be found on the RE4AFAGRi platform Wikipedia page. Today, Africa is described as the dark continent. This can sometimes be a depressing situation. However, opportunities do exist for the future. But what if there was a different scenario? Africa in the future becoming a 21st century sustainable development continent with energy and prosperity for all. Here we see a modeled scenario of looking at Africa from space with universal access to electricity. Join us in the upcoming videos where we show you how to install the software for Onset, as well as a much more detailed introduction of how Onset works, how to run it, and how to tailor it for your scenarios.